Is artificial intelligence just a magical, floating brain in the sky? A ghostly, perfectly clean sequence of mathematical weights and biases hovering happily in an ethereal, brightly lit digital cloud? Or is it actually the heaviest, loudest, dirtiest, and most aggressively sweaty industrial behemoth that human beings have ever dared to construct? This is Critical Path, where we explore stories and innovations about our global supply chain that connect our world to your everyday life. Think about the prevailing cultural narrative of the 21st century for just a second. To hear the technology pundits and billionaire executives tell it, the greatest technological revolution in human history is occurring entirely in a pristine vacuum. We have been socially conditioned to think of artificial intelligence as this ghostly, untouchable force that is completely detached from the messy, grimy, exhausting realities of the physical world. When you close your eyes and picture a modern data center, what exactly do you see? If you are like most people, you probably picture a sterile, silent, glowing hall of sleek silicon brains. You picture machines that think, dream, and generate award-winning art without ever so much as breaking a sweat. It is an aesthetic heavily borrowed from a sleek Apple commercial, all white lights, smooth glass, and quiet hums. But let me tell you, if you were to actually take a crowbar and peel back that sleek, brushed metal exterior of the modern artificial intelligence revolution, you would find a reality that is far more visceral, aggressively loud, and wildly, unapologetically industrial. You would not just find elegant lines of Python code floating in a digital utopia. You would find thousands upon thousands of tons of reinforced heavy-duty steel. You would find hundreds of miles of incredibly thick copper cabling. And you would hear the constant, deafening, literal jet engine roar of industrial-grade liquid cooling systems working desperately, around the clock, to keep the entire trillion-dollar enterprise from spontaneously catching fire and melting into a puddle of very expensive slag, while the entire world has its attention firmly and obsessively fixed on the high-profile semiconductor divas, the flashy, ultra-expensive graphics processing units produced by Nvidia, or the specialized accelerators custom-built by Google. The true, hidden story of artificial intelligence is actually being written by the modern equivalent of picks and shovels. We are talking about the unsung, blue-collar heroes of the massive data center supply chain. We are talking about highly specialized raw materials dug out of the earth, niche manufacturers of heavily reinforced server racks, heavy-duty power distribution units, and massive, polluting diesel generators that serve as the ultimate, ironclad insurance policy against a digital dark age. This entire revolution is not just a triumph of clever software programming by guys in fleece vests. It is an absolute, undeniable masterpiece of heavy, traditional industrial manufacturing and grueling physical logistics. Let us start our journey by wandering into the high-stakes theater of artificial intelligence hardware, where the processor is almost always viewed as the lead actor. The processor gets all the magazine covers, all the stock market bumps, and all the glory. But the fundamental truth of computing is that the processor's performance is entirely, 100% dependent on its supporting cast, specifically, the memory. To truly understand this, we need to look at how a traditional computer architecture actually works. In a normal, everyday computer, the processor and the memory, which is known as DRAM, are essentially like two different corporate offices located at the exact opposite ends of a very, very long, incredibly narrow hallway. Imagine an ultra-caffeinated, super-genius processor sitting at a massive desk, vibrating with raw calculating potential, trying to solve the mysteries of the universe. But every single time that genius processor needs a tiny piece of factual information, it has to send a beleaguered intern running all the way down that long hallway of traditional copper wiring to fetch a piece of data from the memory filing cabinets. As that physical hallway hits its absolute speed limits due to electrical resistance, the hyper-expensive processor ends up just sitting there at its desk, completely idle, twiddling its microscopic silicon thumbs, waiting for the intern to come back with the information it needs to actually do its job. For massive large language models and complex deep learning applications, this physical delay is completely, utterly, and laughably unacceptable. You cannot build a godlike supercomputer if it spends 80% of its time waiting for a file transfer. The ingenious solution to this massive, structural bottleneck is something called high bandwidth memory, or HBM for short. The hardware engineers essentially looked at that horizontal, sprawling office layout, realized it was terribly inefficient, and decided to fire the intern and build a vertical skyscraper instead. High bandwidth memory is a vertically stacked architecture connected by things called through-silicon vias, which are microscopic, laser-drilled vertical tunnels filled entirely with conductive material. By using advanced 2.5D or 3D packaging techniques, they stack the memory chips directly on top of each other, getting them physically as close to the processor as the laws of physics will allow, effectively bypassing the speed limits of standard printed motherboards. This is not just some minor incremental year-over-year upgrade. This is a massive, earth-shattering paradigm shift that provides 5 to 10 times the bandwidth of standard DDR5 memory, all while miraculously consuming significantly less power per bit of data transferred. The entire global semiconductor industry is currently locked in a frantic, sweaty, multi-billion-dollar race to climb this vertical ladder. They are rapidly moving from HBM3 to HBM3E and looking desperately toward the promised land of HBM4 in the very near future. Speeds are reaching up to an absolutely blistering 16 gigabits per second per pin. But, as with everything in the physical world, here is the massive catch. Creating this vertical silicon skyscraper creates an immense, mind-boggling, practically impossible manufacturing challenge. Stacking 12 or 16 incredibly delicate, microscopic silicon dies directly on top of each other is essentially the semiconductor equivalent of trying to build a complex, multi-story house of cards while standing in the middle of a trampoline park during an active, terrifying earthquake. It requires a level of atomic precision that makes brain surgery look like finger painting. And here is the truly brutal part. If just a single die in that massive 16-layer stack has a microscopic defect, a tiny, invisible flaw, the entire skyscraper is absolute, worthless junk. You cannot just swap out the bad flaw. You have to throw the whole incredibly expensive building in the trash. This intense, unforgiving manufacturing difficulty has led to a ruthless, zero-sum dynamic in the global memory market. Major players like Samsung, SK Hynix, and Micron are actually, physically reallocating their fab and wafer capacity. They are moving away from manufacturing the boring, standard memory found in your everyday smartphones and personal computers, and they are focusing all their energy and efforts on high-bandwidth memory. Why? Because high-bandwidth memory currently earns 3 to 5 times higher profit margins. Consequently, the artificial intelligence boom is actually creating a massive, global memory squeeze. It is quietly driving up prices for basic consumer electronics because the big manufacturers are heavily prioritizing the massive, high-margin orders coming from hyperscale data centers. Your next smartphone might cost more simply because ChatGPT needed more vertical brain space. Now please get ready for the most bizarre, hilarious, and frankly unhinged plot twist in the entire history of modern technology. I want you to sit down for this. While the world's most sophisticated engineers are obsessing over microscopic silicon tunnels and memory bandwidth, the entire artificial intelligence industry, this trillion-dollar enterprise that is supposed to redefine humanity, is currently hopelessly tethered to a wildly surprising industrial byproduct. This brings us to the first massive, head-scratching revelation of the supply chain, the Ajinomoto build-up film, or ABF for short. Now, if the name Ajinomoto sounds familiar to you, it is probably not because you are a semiconductor supply chain nerd. It is because you have seen it in a grocery store, or in your pantry, or in the back of your favorite restaurant's kitchen. For well over a century, the Ajinomoto Group has been known globally for a very, very different kind of chemistry. They are the undisputed, heavyweight kings of food seasoning. Specifically, they are the global pioneers in the mass production of monosodium glutamate, better known to the world as MSG. Yes, you heard me correctly. MSG, the magical flavor dust that makes your favorite fast food burger taste like heaven and makes your late-night takeout completely irresistible. Back in the 1970s, researchers at Ajinomoto were messing around in their labs, presumably looking for the next great flavor enhancer, and they discovered that the specific epoxy resins they were using in the production of their food seasonings actually possessed absolutely extraordinary electrical insulating properties. They took this quirky discovery and developed a specialized, highly complex interlayer insulating material that could connect advanced computer chips to circuit boards with unprecedented precision. Fast forward to today, and this material, the Ajinomoto build-up film, has become the absolute, de facto global standard for high-performance semiconductor substrates. It is literally the magical glue that allows complex multi-layered chiplet architectures to function without electrical interference. Despite the futuristic, sci-fi nature of artificial intelligence, it is currently absolutely dependent on a material derived from amino acid science by a food company. And this food company holds an over 90% global market share in this extremely specific, wildly critical segment. Without this MSG byproduct film, the silicon skyscraper of high-bandwidth memory and the complex packaging used by Nvidia would be physically impossible to build. The electrical signals would scramble into absolute garbage, the intense heat would build up exponentially, and the digital dream of superintelligence would simply short-circuit and die in a puff of smoke. It is a delightfully counterintuitive twist. The progress of the most advanced, world-altering technology humanity has ever conceived is physically governed by the chemical production capacity of a Japanese food seasoning company. So what exactly happens to this magical flavor film? The film is carefully sent to a very small handful of highly specialized substrate manufacturers, primarily located in East Asia. These niche companies take the film and painstakingly turn it into the incredibly complex high-density interconnects that actually house the graphics processing units and their massive memory stacks. This market is incredibly terrifyingly concentrated. The top 5 manufacturers hold approximately 70% of the total global market share. We are talking about specialized companies like Ibiden and Shinko Electric in Japan, Unimicron and Nanya PCB in Taiwan, and AT&S over in Austria. The demand for these very specific substrates is currently experiencing a massive, historical supercycle. As artificial intelligence models grow more and more complex and demand more and more calculating power, the number of microscopic layers in these substrates increases, which naturally makes them much harder to manufacture and far more prone to agonizing supply chain snags. This naturally brings us to the fascinating economics of advanced packaging. For decades, the semiconductor industry was governed by traditional Moore's law, which is the idea that we can magically double the number of transistors on a single monolithic chip every 2 years. Well, that law is finally hitting some very hard, incredibly stubborn physical limits. Instead of trying to make a single, massive, wildly expensive chip that will inevitably have fatal flaws, engineers are now creating smaller, highly specialized chiplets and carefully stitching them together on a single substrate. This technique is brilliantly spearheaded by TSMC's chip-on-wafer, on-substrate packaging, commonly known in the industry as CoWoS. This represents a total, fundamental paradigm shift in semiconductor economics. While building a brand new, leading-edge wafer fabrication plant can easily cost anywhere between $15 billion and $30 billion, a state-of-the-art advanced packaging facility can be built for quote-unquote only $2 billion to $5 billion. Yet, despite being the cheaper facility to build, this specific packaging segment is currently delivering a massive 19.6% annual growth rate, significantly outpacing the growth of traditional, old-school wafer fabrication equipment. The technical complexity of stitching these tiny chips together is immense. It involves combining chips from entirely different manufacturing processes, managing insane levels of heat density within a tiny footprint, and using sophisticated laser-guided inspection tools to ensure every single microscopic connection is absolutely perfect. In fact, the sheer desperation for perfection is so high that the demand for this specialized testing equipment surged by an incredible 48.1% in the year 2025 alone. Key players in this space like Amkor Technology, who recently secured a massive $1.6 billion government grant to build a brand new facility in Arizona, and ASE Technology, are essentially the high-end, bespoke tailors of the artificial intelligence world. They take raw, unformed silicon fabrics and carefully stitch them into the high-performance, bulletproof suits worn by the world's most powerful computers. But once you have these massive, stitched-together, heavily insulated, ultra-expensive superchips, where do you physically put them? In the ancient history of traditional cloud computing, which is to say, about 5 years ago, a server rack was essentially just a metal shelving unit. It was a sturdy but entirely unremarkable piece of boring, grey office furniture. You could basically buy one at an industrial IKEA. But in the modern world of artificial intelligence, the humble server rack has been transformed into a terrifying, over-engineered feat of heavy industrial warfare. Because these new graphics processing units consume absolutely enormous amounts of electrical power and generate an intense, horrifying amount of heat, they have to be packed into extremely high-density configurations. If you tried to put a modern artificial intelligence cluster into a standard enterprise server rack, the metal would literally buckle, bend, and completely collapse under the weight, leaving you with a pile of extremely expensive, highly intelligent rubble. Modern artificial intelligence-optimized racks are manufactured by heavy industry giants like Vertiv, Schneider Electric, and Eaton. They are designed to support stationary loads that would absolutely crush a small European car. We are talking about a single 45U or 48U rack that can now easily handle up to 5,000 pounds. That is 2,268 kilograms of incredibly dense, incredibly hot metal and silicon. To achieve this level of structural integrity, manufacturers cannot just use standard sheet metal. They have to use 2.5 mm thick steel, heavily reinforced with extra industrial welds, thick steel gussets, and massive, upgraded heavy-duty casters and levelers just to keep the entire thing from crashing through the floor. And the physical dimensions of these racks are expanding rapidly. Artificial intelligence servers are significantly deeper and wider than their standard predecessors, because they have to accommodate massive, anaconda-sized power cables and heavy, fluid-filled liquid cooling manifolds required for thermal management. Some of these racks now feature a staggering, massive depth of 54 inches. This giant footprint is completely necessary to manage the terrifying spaghetti monster of heavy-duty cabling without obstructing the incredibly critical airflow. Interestingly, many of these modern, ultra-heavy racks are now finished in a stark, bright white powder coat, rather than the traditional, menacing data center black. This is not some sleek aesthetic choice made by a fancy Silicon Valley interior designer. It is a purely functional, life-or-death survival tactic. The bright white finish dramatically improves visibility within the dark, cramped, high-density installation. It allows exhausted, overworked technicians to actually see the ports and cables more easily during routine maintenance, which vastly reduces the risk of accidental disconnections in a mission-critical environment. You really, truly do not want to accidentally trip and unplug a £5,000 rack that is currently halfway through calculating the cure for a complex genetic disease. The history of the server rack is a fascinating journey from simple, dumb vertical storage in the 1960s to the highly intelligent, fortified infrastructure we see today. Back in the 1990s and early 2000s, the focus was just on basic standardization, making sure a server from one company would fit into a rack from another. But modern artificial intelligence racks are now heavily integrated with an array of complex sensors that monitor temperature, humidity, and power consumption in real time, constantly feeding data back to a central brain. Standard catalog racks often cannot handle the insane requirements of a unique cluster, so manufacturers are behaving much more like bespoke engineers, offering fully modular designs and highly specialized security features, like biometric access controls and integrated camera surveillance. The humble, unsung server rack has officially become a smart, £5,000 steel fortress. Now, if the processors are the big, flashy brains of the operation, the networking and cabling systems are the critical central nervous system. When thousands of these processors are working together on a single, massive artificial intelligence training problem, they must communicate with each other constantly and at absolute lightning speeds. This intense chatter creates a massive connectivity bottleneck. Traditionally, this communication has been handled by thick, heavy copper cables. But as data rates climb relentlessly toward 224 gigabits per second, and eventually to an eye-watering 448 gigabits per second, traditional copper is hitting a brutal, impassable physical wall. The underlying physics of standard copper are entirely unforgiving. As signal frequencies increase to these ridiculous levels, the electrical energy simply dissipates and degrades over shorter and shorter distances. This hard physical limitation has led to the rapid rise of active electrical cables, which have tiny chips embedded in them to boost the signal, and a frantic, industry-wide shift toward optical interconnects and photonic fabrics. Companies like Amphenol, Molex, and TE Connectivity are at the absolute beating center of this massive transition. Amphenol, for example, has deeply expanded its role in the data center stack by aligning very closely with Nvidia and outright acquiring specialized cable divisions. They are desperately designing entirely new interconnects, like the USB 4 Gen 3 connector, that must not only handle incredible, mind-bending data rates, but also survive the violent mechanical stress and high-vibration operations of a roaring, vibrating data center. The amazing, profound realization here is that we are witnessing the literal, physical death of the traditional wire. In the very near future, the heavy, cumbersome copper cabling of the data center will be entirely replaced by microscopic pulses of light, moving silently through perfectly clear glass fibers that plug directly into the heart of the processor itself. The picks and shovels of global connectivity are officially moving out of the boring realm of electrical engineering and stepping squarely into the mind-bending realm of quantum physics. But all of this electricity running furiously through copper and glass creates a terrifying, inescapable byproduct: heat. Heat is the ultimate, undefeated governor of artificial intelligence performance. A single, fully loaded artificial intelligence rack generates enough raw thermal energy to comfortably heat an entire, medium-sized office building in the middle of a freezing winter. Traditional air cooling, which essentially just involves blowing heavily chilled air over the hot components with giant, loud fans, is becoming woefully and laughably inadequate. Air simply does not have the physical heat-carrying capacity to manage 100 kilowatts of power per rack. Blowing air on these chips is like trying to put out a forest fire by gently exhaling on it. This sheer thermodynamic nightmare has necessitated the rapid adoption of the liquid cooling revolution. The absolute centerpiece of this revolution is a massive, complex machine called the Coolant Distribution Unit, or CDU. Think of the coolant distribution unit as the mechanical, beating heart of the data center's cooling system. It violently and constantly pumps a specialized liquid coolant through a massive, closed-loop plumbing system, delivering it directly to small, highly conductive cold plates that sit perfectly flush on top of the extremely hot processors. Why liquid? Because liquid cooling is roughly 24 times more efficient at transferring heat than air. This incredible efficiency allows modern data centers to achieve a power usage effectiveness rating below 1.05, which is practically miraculous. A very small handful of specialized, highly industrial companies have emerged as the absolute leaders in this critical segment. Panasonic, for example, recently launched an entire liquid cooling business specifically targeting hyperscale data centers, developing massive units with cooling capacities completely exceeding 1,200 kilowatts. Other key players include Asetek, Cool IT Systems, and Motivair, which was actually just acquired by Schneider Electric in a massive industry consolidation move. Another company, AIRSYS, makes a specialized unit that offers triple-layer mechanical redundancy and an industry-leading approach temperature of just 4 degrees Celsius. But for the most extreme, mind-bending, power-hungry workloads, even pumping cool liquid directly to the chip is still not enough to stave off a fiery disaster. This has led to the terrifying rise of immersion cooling. This is exactly what it sounds like. The entire multi-million-dollar server is fully submerged and literally drowned in a giant glowing tank of non-conductive dielectric fluid. Companies like LiquidStack and Green Revolution Cooling are pioneering this wild sci-fi approach. It allows for perfectly uniform heat dissipation across every single component and eliminates the need for any spinning fans entirely. This is the ultimate, brute force industrial solution, pumping thousands of liters of specialized chemical fluid through high-tech vats just to keep a glowing digital intelligence from completely vaporizing itself into oblivion. However, despite all of this amazing technology, the absolute most significant physical bottleneck in this entire artificial intelligence boom is not the processor, it is not the 5,000-pound server rack, and it is not the massive vats of liquid cooling fluid. The ultimate, terrifying bottleneck is the electrical power grid itself. A single, hyperscale artificial intelligence data center can easily consume as much electricity as a medium-sized, bustling city. Yet, our global electrical infrastructure is essentially operating on a rusty, mid-20th century industrial clock. This immense, practically insatiable strain has created what terrified industry insiders are quietly calling the 120-week wall. To connect a massive, brand-new data center to the electrical grid, operators cannot just plug it into a giant wall outlet. They need gigantic, custom-built, high-voltage transformers and highly specialized switchgear. But here is the brutal, inescapable reality of the physical world. While artificial intelligence software code can be updated globally in a matter of seconds, and processing chips can be manufactured and shipped in a few weeks, a single 500 kilovolt transformer now takes up to 120 weeks to manufacture and deliver. 120 weeks? That is more than 2 entire years. You could literally adopt a tiny puppy, train that puppy to fetch your slippers, watch that puppy grow into a wise, grey-muzzled senior dog, and you would still be sitting there waiting for your electrical transformer to arrive. This agonizing delay is rooted in a fundamental, inescapable material constraint: the massive, global scarcity of grain-oriented electrical steel, or GOES for short. Grain-oriented electrical steel is a highly specialized iron-silicon alloy that is meticulously engineered to have very specific magnetic properties that perfectly minimize energy loss during massive power conversions. Manufacturing it is not simple at all. It is a deeply complex, multi-step metallurgical process that requires extreme, microscopic precision. Right now, there is a massive global deficit in the production capacity of this specialized steel. In the United States alone, there is exactly one single plant that produces the specific type of steel needed for these giant data center transformers. The physical limits of metallurgy are completely non-negotiable. The tech bros in Silicon Valley are used to moving fast and breaking things. They want their software updated in milliseconds. But the physical universe does not care about agile development sprints. The physical universe says you absolutely cannot use software updates to speed up the high-precision rolling and specialized, excruciatingly slow curing cycles required for heavy steel and transformer oil. This has created a massive, terrifying 10 times latency gap between the incredibly fast-moving world of digital bits and the excruciatingly slow world of physical atoms. If the heavy steel cannot support the shiny silicon, billions of dollars in tech investments run the very real risk of becoming incredibly expensive, useless paperweights. So what happens if the grid actually fails? Because artificial intelligence training runs are so astronomically expensive and deeply time-consuming, even a momentary power flicker that lasts a fraction of a single second can result in millions of dollars of lost work and corrupted data. To prevent this absolute catastrophe, the futuristic artificial intelligence boom has simultaneously, and quite ironically, turned into a massive boom for one of the oldest, loudest, and dirtiest technologies on planet Earth, the diesel generator. Take the state of Virginia, for example, which is the undisputed largest data center market in the entire world. It is the beating heart of the global internet. In Virginia alone, there are over 10,500 permitted diesel generator units sitting quietly outside these massive, windowless data centers. Together, they have a total, mind-bending backup power capacity of 27 gigawatts. Let us put that staggering, ridiculous number into perspective. 27 gigawatts is completely equivalent to the total power usage of 20 million United States households. 20 million! Yet, all of that immense, dirty diesel power is sitting right there in the backyard of a state that only has roughly 4 million actual homes. It is an arsenal of internal combustion, just waiting for the lights to flicker. These colossal generators, produced by heavy equipment legacy companies like Generac and Kohler, are the ultimate, bulletproof insurance policy. They are perfectly designed to sense a grid failure, roar to life with deafening volume, and take the full, massive electrical load of a data center in a matter of mere seconds. But if a true, sustained grid crisis hits, the real-world logistics of keeping these digital brains alive are absolutely terrifying. If the electrical grid goes down for just a single 100 megawatt artificial intelligence data center, that single facility requires nearly 7 million gallons of diesel fuel per day to maintain continuous operations. In the event of a major regional power outage, just meeting the emergency, life-or-death demand of the Northern Virginia data center hub would require an estimated 40 fully loaded fuel trucks per hour to constantly, desperately deliver enough diesel to keep the generators running and the artificial intelligence alive. This is the final, mind-bending revelation. The most advanced, ethereal, futuristic digital intelligence in human history is ultimately and totally backed up by a massive, 20th-century logistical fleet of diesel trucks and heavy combustion engines. Artificial intelligence is not just elegant code floating in the ether. It is a raging thermodynamic engine that, in its most desperate and critical moments, runs on the exact same dirty dinosaur fuel as a long-haul semi-truck driving down the interstate at 3 in the morning. The picks and shovels of the tech revolution tell a story that is vastly, wildly different from the glossy, minimalist keynote presentations we see streamed online by billionaires in sneakers. While the world's attention is captivated by the elegant complexity of neural networks, the heavy reality is that this is an industrial project of completely unprecedented physical scale. Artificial intelligence exists because a Japanese food seasoning company discovered how to turn their chemical MSG byproducts into a microscopic insulating film. The entire intelligence is securely housed in 5,000-pound steel racks that are wildly over-engineered to survive loads that would crush a normal office building into dust. The silicon brains are kept from melting down by industrial-grade liquid pumps and massive immersion tanks that treat the sterile server room like a high-tech chemical refinery. The actual pace of human progress is completely gridlocked, not by lazy software developers, but by the strict metallurgical limits of electrical steel and a 120-week waiting list for iron transformers. And the ultimate, unshakable reliability of the cloud is provided by a massive, polluting fleet of thousands of diesel generators and a never-ending convoy of fuel trucks. The incredible truth is that the more advanced our technology becomes, the more deeply it relies on traditional, heavy, industrial manufacturing. Behind every magical, instant chatbot response is a screaming diesel engine, a house-sized transformer made of incredibly rare specialty steel, and a thin layer of epoxy resin from a food seasoning factory. Artificial intelligence is simply the heaviest thing we have ever built. Think deeply about this wild contrast between the digital illusion and the physical reality. What aspect of this hidden, heavy industrial infrastructure surprises you the most? Do you think our physical power grids, our steel supplies, and our water resources can actually keep up with our limitless digital ambitions? Or will the physical world ultimately put a hard, immovable speed limit on the future of artificial intelligence? Let us know your thoughts down in the comments below. Thanks for listening and watching. Please like and subscribe, and make sure to check out our other videos about the global supply chain.